Okay, welcome. We are going to do a lot of problems today. We've been doing a lot of theory and haven't really been hitting the problems very hard. And I chose homework problems to make life more fun. Diana, I decided, sure, why not? So the assignment that was due on Wednesday, I extended it for everybody to be due the same time as tonight's assignment for those who had difficulty with the first the problem number 3 and didn't have a chance to ask. Let me just talk about that problem number 3. I don't have it here in my lecture slides, but problem number 3 has a sequence of chambers with manometers between them. Yeah, it was very smoothly drawn. And you have a height difference in fluid from one side to the other. So what does it tell you if you have a difference in the fluid height from one side to the other on a manometer? They have different pressures. Which one is higher pressure? The lower one is the higher pressure. Because pressure is force over area. The side that has a higher force per area is going to be pushing harder, and so it moves away from it. And then what's the equation that relates the pressures if you have a difference in height for a fluid? So by Pascal's principle, the pressure here has to be the same as the pressure here. And then I have this height difference of H1 of fluid. What's the equation for the pressure difference if I have a height difference of H1? Yes, delta P is rho GH. So the entire solution to this, every step of it, is simply applying delta P is rho GH between adjacent chambers. And so you know what the pressure in A is, and you know what height 1 is, so you can use that to calculate the pressure in B. And then you know the pressure in C, and you know the pressure in B, so you can use that to calculate the height difference between B and C. And likewise. Now I told you, of course, it gives you the wrong answer for the last one. I don't know how the person who did this had the brain fart, but I will go through and hand grade it on Sunday. And if you got the correct answer the first try, I will give you full credit. If the program gave you full credit the first try, you won't get full credit. Right, because it's wrong. All right, that said, now that Maxwell's here, we can start doing some problems. And yeah, these are the homework problems due tonight. So problem number 1, bird bones have air pockets in them to reduce their weight. This also gives them an average density significantly less than that of the bones of other animals. Suppose an ornithologist weighs a bird bone in air and water and finds its mass is 43 grams, how would they find the mass is 43 grams from weighing it? How would he find the mass is 43 grams if he weighed it?
And you do kind of the same thing we did for lab the other day?
Yeah. Weight is mg, so if you measure the weight and you divide by g, you can calculate what m is. And then it says that it has an apparent mass when submerged of 3.5 grams. Apparent mass. It's not its actual mass because the mass is how much stuff is present. It's an apparent mass because he did the same thing. He weighed it in water just like you did in the lab. And then he divided that by g to get an apparent mass because it's not a real mass. It doesn't associate with mass at all. Then it asks us what mass and volume in grams of water is displaced. So the first thing you have to ask yourself when you're approaching any problem is what's the concept involved here? So what concept would relate those measurements, the mass of the bone and the apparent mass when it's submerged. Okay, we're dealing with buoyant force here. And what is Archimedes' principle, the thing that tells us about buoyant force? What does it tell us?
Buoyant force is equal to volumes.
Okay, put it in simplest terms, it's the weight of the fluid displaced. So the buoyant force is the weight of the fluid displaced. Well, we know the mass difference for the buoyant force, right? In other words, force buoyant is equal to the weight of fluid displaced and so if I want to find the mass of the fluid displaced, how do I go from the weight to the mass? Just like we did a moment ago, how do I go from weight to mass? I divide by G. So the weight of the fluid displaced divided by G is going to be the mass of the fluid displaced. But the force buoyant divided by G is the difference in those two apparent masses, just like what we did in lab. The force buoyant is mg minus the apparent mass times G. So if I divide those by G, it's just the difference in masses. So this is well, notice I can cancel these G's. And so what's the mass of my fluid displaced? It's going to be the actual mass minus that apparent mass. So in my case, it's just 43 minus 3.5, which makes it 39.5 grams. This is all applying Archimedes' principle. Just like what we did in lab. And this is exactly like what we did in lab. Number 2, what is the volume in cubic centimeters displaced by this bone? Actually, it doesn't say displaced. What is the volume in cubic centimeters of the bone? Did the bone sink or float? It's sunk. That's an important aspect to answering this. If it had floated, it would be a much harder question. But because it sank, I know that it displaced a volume equal to its own volume. So, what's the volume it displaced? I know that force buoyant is equal to density of the fluid times the volume displaced times G. So that means the volume displaced is equal to the force buoyant over density of the fluid times G. And the force buoyant over G, we just calculated was the 39.5 grams. 39.5 grams divided by the density of water gives me the volume displaced. I forgot I said these out loud, but I'm going to write them down. The density of water is in grams per centimeter cubed. Is that. So, wow, just comes out to be 39.5 centimeters cubed. Ain't that right?
I believe so.
Finally, what is the average density of the bone in grams per centimeter cubed? If I know the volume and I know the mass, how do I find the density? Just like in lab, right? You did all of this for lab. How did I find the density in lab?
By volume.
So what number do I use for mass here? The 43. The actual mass. Oops, not grams per centimeter. That was centimeters cubed. So I'd have 43 grams divided by 39.5 grams per centimeter cubed, which would give me, I don't know, something a little bigger than 1 cubic centimeter. Any questions about this problem? Everybody down with this problem? All right. Let's go on to the next one, which conveniently enough is problem number 2. Suppose a woman, now to keep my subscript straight, I decided to use a person instead of a woman, not trying to take away her womanliness, but trying to distinguish between water and woman. I'm using P for person instead of W for woman. So suppose a woman floats in fresh water with 3.95% of her volume above the surface of the water. What is the density in kilograms per cubic meter of the woman? Any ideas?
Use Archimedes Principle again.
We're going to use Archimedes Principle again. Now, I was lazy last time because we did it all in lab. But this time I'm going to draw my diagram like any good student should. There's the person. They're floating in water. What forces are acting on this person? Okay, we have the water pressure. We have the force buoyant. Change color. Force buoyant is equal to the density of the fluid times the volume displaced times G. What else is acting on the person? The force of gravity. Force of gravity equals mg. But now that we're doing things with fluids, we often, instead of putting m, what do we use? Yes, rho volume. So that's equal to density times volume. And this is not the volume displaced. This is the volume of the person. And the density of the person times G. Now, if the person floats, what else can you tell me? She is in equilibrium. Equilibrium means the sum of the force is 0 and the sum of the torques is 0. Well, in this case, it's pretty clear we're not dealing with rotation. So I'm just going to do sum of the forces in the y direction is equal to mass times acceleration in the y direction is equal to 0. Equilibrium means acceleration y is 0. So that means I have density of the fluid times the volume displaced times G is equal to the density of the person times the volume of the person times G. What's the first thing you would do at this point?
Check to see what we're looking for.
Check to see what we're looking for. What are we looking for? Density of person. So I'm going to divide by everything that's not the density of the person on the right-hand side. And we see the G's cancel. And I have the density of the person is equal to the density of the fluid times the volume displaced divided by the volume of the person. This is all good physics. What do I know?
That.
I know this equation. Density of the fluid. I know the density of the fluid because it's water. What's the density of water? One what? 1 gram per centimeter cubed, or 1,000 kilograms per meter cubed. So I know, this is why we're always told to put down what we know. I hit the green button. You guys can see that, right? The green button's highlighted, it just didn't take. I just put 10 to the third kilograms per meter cubed because it's the quickest way to write 1,000. Okay, what else do I know?
You know that only like 96.5.
Okay, I know that 96.5% of her is, or 96.05% of her is displacing water. So I know, now you might ask, where did she get the 96.05? She is 3.95% above water, which makes it 100 minus 3.95% equals 96.05% below water. That's where the number comes from. So that means that we know that the volume displaced is equal to 0.9605, going from percent to a number, times the volume of the person. Well, that's all I need, because I'm looking for volume displaced over volume of the person. If we take those two numbers, what is volume displaced over volume of the person? Anyone? 0.9605. So this is just equal to 10 to the third kilograms per meter cubed times 0.9605, which any one of us could multiply in our head, I hope, and get 960.5. So, starting with what looked like some really minimal information, we have now discovered that the density of the woman is 960.5 kilograms per meter cubed, or 0.9605 grams per centimeter cubed. Her density is less than the density of water. What does that mean if the density is less than the density of water? She floats in the water, which was where we started the problem, just getting to the end, make sure we make that connection. Now, part B, what percent of the volume is above the surface when she floats in seawater, which has a density of 1,025 kilograms per meter cubed? How could we find that? Is what? I still can't hear you. Okay, we have our equation that's already done. We now know density of the person is, well, using the numbers they have, 960.5 kilograms per meter cubed. And we know the density of the fluid is 1025 kilograms per meter cubed. And from this relationship that we worked out right there, the volume displaced over the volume of the person is equal to the density of the person over the density of the fluid. So that's 960.5 kilograms per meter cubed over 1025 kilograms per meter cubed. So what percentage of her volume is below water? Requires a calculator. What is it? Somebody?
Uh, 93.71. Oh, yeah, 0.937.
Okay, so that's the ratio. The question asks what percentage is above water?
So take that, subtract it from 1.
Right. 1 minus this gives me the amount that's above. convert that to percentage, that's 6.29% is above water. Notice when she's in seawater, she floats higher. What if she were to go to the Dead Sea? It has a higher density still, so she would float even higher. Now I want you guys, as tables, you can turn around and join them if you want, to calculate what percentage of an iceberg is above the water level. An iceberg is made out of pure water. And pure water, when it freezes, has a density of 917 kilograms per meter cubed. And we're still going with the seawater having 1025 kilograms per meter cubed. So what percentage of the iceberg is above water?
Wait, what is the PHYS?
What is what? Oh, row ice, the density of ice. Can I go back to the question? Yes, ma'am.
Yep, one was the answer. And then timeline.
I was like, what did you do with this?
He did that.
It's true, I did, but simply using part B, that will get you up.
That much.
And point to what?
Why?
I got the ball.
Talk about how you did it.
I know, I can't use mine, and I don't know how to do anything, but I was.
So you want to do some forces in the X.
Wow.
And no forces in the X, so don't worry about that.
What's the
I
water?
do. Density of my fluid, density.
You might want to join better.
Oh my God. Exactly.
What is this?
I have no idea.
How about if you to do the exact same thing, so just do 975.
Why?
Yeah. 89%. One was that good.
Oh, I just got.
If you were in the last one,
Why am I dividing? Why am I dividing?
Because you have volume displacement
So,
over volume
I'm dividing this.
instead of person now, it's going to be iceberg.
Oh.
Is equal to density of iceberg divided by the density of fluid.
You wouldn't laugh like that when you're done.
Because they're not proportional, yeah. They're not, yeah. It's not like the volume displaced of the.
Well, yeah,
The volume person is on the bottom, and the density person is on the top.
the place it came from was from that.
But isn't there a formula that says that?
Well, it comes from the work we did. But there's no general generic formula.
How do you have the formula?
The formula is Archimedes Principle, that the buoyant force is equal to the density of fluid times the volume displaced times G. That's the formula. And then from that, we got the specific case formula for floating. If it's not floating, of course, that wouldn't be the correct equation. So you guys got it? Yep.
do you understand what?
You got it?
I think, okay.
You guys get it figured out?
Yeah.
Okay, so as one, what percentage of the iceberg is above water?
89%. Nope.
I heard 100%, 89%. Do I have a third answer?
7.5.
10.5%. Okay. We didn't have that many sig figs. So roughly 11% of the iceberg is above water. And that's why we have phrases like, that's just the tip of the iceberg. That's saying, if you're in a ship and you see an iceberg, it doesn't look all that big compared to what it really is because you're only seeing 11% of the iceberg. Okay, next problem, surface tension. This is the problem with making an assignment before lecture. I made this assignment before lecture for Andy, and then I didn't have a chance to talk about surface tension in lecture on Wednesday. So this is new to you. Now this problem, you don't have to understand anything to solve this problem, which is unfortunate because, of course, we want you to understand things. So first, oh man, I had all my visual aids. They're sitting on my desk. I'm going to be right back. My visual aids for describing surface tension.
All right, everybody, what's a glycosidic bond?
Type Andy.
What's a glycosidic bond?
I'm like I said, inositol glycose or
What'd you say?
type B has the glass.
As soon as I walk out, I hear Max say, "All right, everybody." Okay.
It's two types. O and N.
Shoeless.
Which one's O?
Oh wait, that's what
Tension. Tell me what things you know about tension.
It's tight.
It's tight.
What's that word? Taunt. Or it's taunt.
Taunt.
Taunt. With an N.
No.
No N?
No way.
Taunt is ha ha ha.
Max doesn't know what a glycosidic bond is.
All right.
That's good.
Oh.
That's an example of taunt. Okay, so taunt. T-A-U-T. Okay, what about the force associated with tension?
It's towards the end.
Okay, the force of tension is always in the direction the string leaves an object with a magnitude equal to the tension. So if I put the string around her water bottle, I have the string coming off in two locations, and it's applying a force equal to the tension in the direction the string leaves location. Surface tension is called surface tension because it's the same concept. Instead of having just a little string, I now have a surface. So I have this for a two-dimensional surface. And if I were to put this around her water bottle, then I would have my forces spread out over the length of contact. Right? It's not just one location coming out, it's over the length of contact. But it would still be in the direction that this is leaving her water bottle. And so that's what's going on with surface tension. With surface tension, you're dealing once again with the adhesive force, the force that is making object A adhere to object B. And the force in general is force surface tension is equal to gamma times the length of contact, where gamma is the thing we call surface tension. Notice since force is gamma times L, then gamma must have units of force over length, so newtons per meter. Now in this problem, we have a wire. So here's a cross-sectional view of the wire. And I have a film that is leaving the wire above and below. Now I have water all the way in between, but it's only at the edge of contact that we have that surface tension force. So I have the top edge has a force of surface tension. What direction is the force of surface tension going to be on the top edge? Left, right, up, down, in, out. Okay, we got it on the third try, but these were just guesses. Going back to tension, what direction was the force of tension? Whatever direction the rope is leaving. And so at the top, what direction is the water leaving? To the left. Right, the water is leaving this surface in that direction. What about the bottom? Also to the left, because the water is going this direction, so force, surface tension, bottom. Each one of those is going to be equal to gamma times the length of the wire, because that's the equation for the magnitude of the surface tension force. These two vectors are in the same direction. Any question? No. These two vectors are in the same direction, so it's pretty easy to add them up. So 2 gamma times L is the magnitude of the surface tension acting on that wire. Now, in this equation, just to make sure we're really clear, what is gamma?
The yellow, Y. Oh, never mind.
Surface tension.
The surface tension, yes. What is L? The length of the contact between the wire and the water. And 2 is because you had it from the top side and the bottom side. And of course, the equation was given to you right here, which is why this problem took no understanding, because they gave you that question. Okay, what do you not understand? It's important.
No, I understand it.
Oh, okay. I thought you said I still don't understand.
No, it's just I didn't look at that, so I just wanted to let that out the first time.
Okay, so calculate the surface tension of the liquid. Given this equation that I circled, which we've now derived why they gave us that equation, how do I find gamma? Force over 2 length. So in my case, it's 3.05 times 10 to the minus 3 newtons divided by 2 times 2.5 centimeters. I don't want my answer in centimeters, so I'm going to change it right now to 0.025 meters. So divide by 0.05 means multiply by 20. So 3.05 times 20 would be 6.1 times 10 to the minus 2. Whoops, I did both. So it turns out that one was really simple, but we didn't talk about surface tension in class. And so now we have. Any questions about how surface tension works? Y'all feel comfortable with that problem? Excellent. It could be.
This exact problem.
Well, it's never going to be this exact problem. That would defeat the purpose of a test.
I mean, yeah, you're right.
So now let us apply this to a different situation. And I know, Sarah, I think I explained this in my email to you.
Yes.
With everything except for the last equation rendered incorrectly. I don't know what
I
happened
don't know
there.
what happened.
So now we're asked about capillary action. Capillary action, let's start by zooming in on this picture. And apparently that's all I'm going to zoom in. Why is the water higher in that tube than it is elsewhere? Because of?
Small radius.
Okay, small radius is a correct application, but what is the overriding rule or cause that makes it so that occurs? The concept.
Surface tension.
It's surface tension. This is another surface tension problem because surface tension is the root of capillarity. So if we take this, what is the pressure right there? H would be a height. It's open to the air. So it's going to be atmospheric pressure. What is the pressure right there? Hey, Judith.
Also 1 atmosphere.
Also 1 atmosphere. Why?
Because it's open to the atmosphere.
Okay, Pascal's principle said that at any elevation in a continuous fluid, the pressure is the same. So that's the same elevation as outside of the tube, which was at atmospheric pressure. And so that needs to be atmospheric pressure. And now, of course, we're all astute enough to think we have a problem, because we know the pressure difference for a column of water is rho GH, right? And so if this was the whole problem, we would say, oh, rho GH is equal to either 0 or not 0. Right? That would be a problem, wouldn't it? But there's more forces involved here. What other things do we have involved? I have this column of water. Okay, we have surface tension acting. Where's surface tension acting? The point of contact between the water and the glass. And when I say the point of contact, I mean where it goes from not contacting to contacting. It's not everywhere it's contacting, it's that point where it goes from contacting to non-contacting. So it's acting at the top, and the problem tells us to assume that the water is vertical at that point of contact. So if the water is vertical at that point of contact, what direction is the wall pulling on the water? The water is, well, let's start with the question the way we've asked it before. What direction is the water pulling on the wall? The direction in which the water is leaving the wall. What direction is the water leaving the wall? Down. So the water is pulling down like this on the walls. Because of surface tension and because it's being pulled down by the other force. Yes, that's the other one. We have a force of gravity that's mg, right, for this column of water. And so that's what's causing the downward pull. So we have a force of gravity that's pulling down, and we have a force upward that's the force of surface tension pulling the water up. It's important to look at that angle because that angle could have been, 30 degrees. It wouldn't be the maximum height. Capillary action should be vertical. But you have to look at the angle. So that was straight up. So we have force of surface tension up, and we have force of gravity down. So if I define up as the y direction, okay.
What is happening?
There, it came back. It has something to do with layers. That's all I can say. So I'm going to do sum of the forces in the y direction. That's beautiful. And so I have my upward forces are the force at the bottom plus the force of surface tension. The downward forces are the force at the top and the force of gravity. Apparently I missed one stroke. Not bad for not being able to see what I was writing. And if this is staying stationary, what do we know the sum of the forces is going to have to add to? 0. So this is equal to 0. Well, the force at the bottom is equal to the pressure at the bottom times area. The force at the top is equal to pressure at the top times area. But we had pressure at the top and pressure at the bottom were both 1 atmosphere. So that means force bottom and force top are the same magnitude. The directions are opposite, so those two add to 0. So what we're left with is rearranging the force of surface tension equals the force of gravity. What's the equation for the force of surface tension? Blank times blank.
Force of gravity is mg.
That.
I wasn't asking about gravity yet.
Oh, that.
It's gamma times L. So force of surface tension equals gamma times L. What is the length of contact between water and the wall of a cylindrical tube?
Circumference of the tube.
The circumference of the circle. What's the equation for circumference of a circle?
Pi r 2 pi r.
2 pi r. So there's my force due to surface tension. What about the force of gravity? Go ahead. Okay, it's mg. Or as we often do with fluids, what did we replace m with?
Rho v.
And what's the volume for a cylinder?
Your thing times your height.
Area.
Area times height. The area of a circle is pi r squared. So there we go. In all of the gory detail. So putting force of surface tension equals force of gravity, I have gamma 2 pi r equals rho pi r squared hg. What am I solving for? We've gone so far we forget. We're solving for what's the height of the water pulled up in the column. And so I want to solve this for height. What mathematical step should I take to solve this for height? Divide by everything the height is multiplied by. Rho pi r squared g. And you immediately see my pi's cancel. 1 r cancels. And I'm left with h is equal to 2 gamma over rho rg. And of course, this is a specific solution if you have a cylindrical tube. If you had a rectangular tube, it would be different, right? Because you would have a different length of contact. And so now we just put in our numbers. It says the surface tension of water is 0.0728 newtons per meter. Divide by the density of water, 10 to the third kilograms per meter cubed, times the radius, and it says we have a diameter of 1.6 centimeters. That means the radius is 0.8 centimeters, half of the diameter, or 0.008 meters. G, 9.80 meters per second squared. And so when you calculate all that through, you get the actual height that it will pull the column up. Is that going to be a big number or a small number? Pretty small. I'm actually going to calculate it because, hey, I've got a calculator in my hand. According to my work, that's 1.86. Well, excuse me, 1.86 millimeters. I automatically converted to millimeters in my head, not thinking that we needed it in meters. So that's how capillary action works. I talked about capillary action very briefly in class, but we didn't do any calculation on how that works. So here we've done the calculation on how capillary action works. And then we have second part, what is the radius in meters of the glass tube on the right if it raises water 4.2 centimeters. So part B, I'm going to forego part B, but for part B, you're just taking the same equation, solving it for R given H. Problem 5. You have water coming out of a spigot. We make some magical rules in this problem to make it easier for you to do. So don't worry about magic, just play along. So it says the water comes out and it has a speed at the top equal to, in my case, 0.495 meters per second. And it has a diameter at the top of 1.6 centimeters. Part A says, what's the flow rate? Well, from class on Wednesday, we did the flow rate. What's the equation for flow rate? Q is equal to
A times velocity.
area times the velocity. Well, times speed, because it's not a vector. At least not the way I'm doing it. What's the area of a circle?
Pi r squared.
So that's pi r squared v. I just put 0.016 meters over 2 for the radius. So there we have the flow rate. And given that we only have 4 minutes left in class, I'm not going to put this in the calculator this time. Go on to part B. Was the diameter in centimeters 0.200 meters below the faucet? Neglect any effects due to surface tension. Now, when it says that, this is part of the magic. What is surface tension doing?
It's holding it together.
It's holding the water together. If you truly neglect the effects, then you're going to have a more difficult time. But what we really care about is what happens to the water as it falls.
Speeds up.
Okay? It speeds up, and because the flow rate must remain constant, it must shrink down in diameter. So you have the same flow rate at a higher speed. So if I'm going to calculate what the diameter is, what's the first thing I need to calculate? The velocity final. This is water falling. Water falling is no different than scissors falling, except for it's less dangerous.
Consider.
So how do I find the speed 0.200 meters below?
Kinematics.
Okay, one way you could have done it would have been using the Bernoulli equation, but that's kind of overkill. I could just simply say V final is equal to, well, I don't have time now, do I? So which kinematic equation do I need?
The final equal, the initial squared plus 2a squared. No. Delta to x. Or double y.
Delta y is vertical. So we put these in. That's V0 squared plus 2 times minus 9.80 meters per second squared times minus 0.200 meters. Why is my acceleration negative? Because it's downward. Why is my distance down? That's what David said, because we're also going down. Acceleration of gravity is down and we're going down. So negative makes it positive. Your V final is faster, and then you go back to the same equations we had up above. And look, I was going to do this problem, and then I was going to look at the homework problems from the next assignment, the one that this is due on Monday because it's going to help you on the test to do these problems. So that's why I'm not postponing it to Wednesday, because I want you to do the best you can on the test. But let's look at this first one. It's actually problem 4 in the assignment, but it's actually now problem 3 because I changed one. Water flows smoothly through a pipe with various circular cross sections of diameter 2D, 6D, and D. So if it moves smoothly, what does that mean?
It's continuous. It's not.
It's continuous. It doesn't have any bubbles or gaps in it. If it had bubbles or gaps, we would have called that turbulent flow. We call this laminar flow. It flows in layers if it's smooth. So as the water flows, where is it fastest and where is it slowest?
Fastest in section 3.
Fastest, where is it slowest?
Section 2.
Okay. Because the flow rate is, and that's part A, how's the flow rate vary?
It does.
The flow rate has to be the same throughout because there's no gaps, no cavities. So the flow rate is the same everywhere, but the section with the highest speed then is going to be the one with the smallest area, D,
And then, of course, it asks for the ratio of the speeds. Well, you just use that Q is equal to AV to find how the speeds relate. And then, which section has the largest pressure?
That'd be section 3.
Pressure plus 1/2 rho v squared plus rho gh is constant. So if pressure is the highest, what does speed have to be? The h is zeros and all over. So if pressure is the highest, what do I need v to be? The lowest. And so that's how you do the calculation. Pressure is the highest, v is. Yeah. All right. Have yourself a merry day and a happy Sabbath.